So to begin, we're going to view the block diagrams, both the level 0 diagram and the level 1 diagram, and then the UML diagram for the program. So here we have the level 0 block diagram. We have two inputs, that's the button press and the watchdog timer. Button press is a manual reset of the system by the user, and then the watchdog timer is the system self-reset. Then there's the actual flash memory program, which it clears and writes 120 kilobytes of and to flash memory. And then the output is the LED blink, and it indicates the success or failure of memory clear and write. And this is the actual program where I wrote today. And then we have the level 1 block diagram, which is a bit more advanced. We have the switch input subsystem, which is the actual subsystem for the button press input. We have the flash memory program, which as before clears and programs one sector of data. It has two inputs, of course, the button press from the preceding block along with the watchdog reset, which comes from the watchdog timer controller right here. And then there are three outputs. That is the initialization of the watchdog timer, and there's the reset of the watchdog timer, and then there's the blink LED output here. And then the LED output subsystem essentially just chooses whether or not to blink a red or green LED contingent upon this blink output. The program dictates whether or not it will pass or fail the flash memory program, or if it receives a button press which would cause a red LED output. And we can see that more in this UML diagram here. So right here, the way the program starts is it starts by holding the watchdog timer. Then it initializes memory access. We initialize ports. We then initialize and start the watchdog timer. We clear the watchdog timer and blink the red LED as a sort of initialization, and then clear it again. If the program detects a button press, it will go back to blinking the red LED. Otherwise, it will proceed as normal, clear again, unprotect a sector address, clear said sector, enable flash memory program, write to the sector, protect the sector, then blink the green LED, and then it exits the continuous while loop, and if there is a button press detected, it will either blink the red LED or keep running. So let's look a bit at the program. So here we have the actual program. Essentially what we have in main is the same thing as the UML diagram described. We hold the timer. My program goes through a memory setup, which is defined in memaccess.c. It sets the core voltage level, sets the wait state, and actually sets the frequency for the the memory, not the watchdog timer. There's also a port setup. So I have my ports properly set up. Port 2, pin 1 is configured for the red LED. Port 2, pin 2 configured for the green LED. And then port 1, pin 1, or pin 2 as an input for button presses. We enable the pull-up resistor. Then I define an array of different macros for sectors. The MSP432 has inherent macros for sectors when accessing flash memory. And so I created an array to make things easier and cleaner. 31, well, technically 32 sectors would equal 128 kilobytes. That is all the sector addresses for bank 1, which is the first flash memory bank. So we clear the timer and we blink the red LED. We turn off the green LED first. It goes through a 1 second sleep, and then it turns off the red LED, so we have a good blink. And then it enters this while loop. This while loop is the actual meat of the program. Oh, one more thing. The watchdog timer, which was initialized up here, is defined in here. My watchdog.c file, and it actually has, it starts the timer and it sets the clock iterations. And it also tells the system that if the watchdog timer activates, it will go through a soft reset. Anyway, back to where we were. This while loop is continuously running. It clears the timer. If there is a button press, it exits the while loop and blinks the red LED again. Otherwise, what we do is we create a more or less empty data set, dummy data set of information, and it's a 4 kilobyte data set. We set the value to 0x85 for this data set, and then for 32 iterations, or 32 iterations, we actually stop the timer so that I can go through this process. I created this integer so that it selects a part of our array, which was defined up here, an element of our array, the appropriate one from the for loop, and then it will delete and write the data. I created a delete and write function, which is defined in memaccess.h. It takes the data set as well as the selection from the array, as well as sector. Sector was defined in here as it's basically the start of bank 1. It's defined in a macro over here. Sector start is the first address for bank 1. And in mem delete and write, we have we unprotect each individual sector. We then erase said sector. Then we enable programming of the sector. We then program the simulated data, the dummy data, into the sector, and then we protect it. And it goes through this 32 times. And then with each sector, there's an increment of the sector, since this function, the function program memory requires a particular address. We add by x 1000 the sector increment to get to the next sector address, since x 1000 is the offset. And then afterwards we clear the timer again to allow for a blinking green LED so that it can successfully, it can show that the entire for loop was executed successfully. Otherwise it blinks red if either the timer goes off before this happens, or if there is a button press, which simulates the same scenario. So the next step, of course, is to make sure that we have all of our files available. Functions.h, which is my big header file, main.c, memaccess.c, ports.c, etc. And we debug it, so upload it to the board. And it might take a little bit of time to load. So if we begin running it, we get blinks from the green LED, but as soon as I push the button, which should make it exit that while loop and essentially cause the watchdog timer to time out, our program actually stops, and the moment I resume it, I get a red LED blink. So here, well, down here, we have the MSP432 doing as it should. It is quite a bit shorter than 1 second due to some issue with timing intervals, but when I hit the button, we get a red LED.